So good morning.
Morning.
All things small and consequential. We're going to start with Paul because editing the journal, and you float among all of these fields. So I wonder if it would be good for you to give us a sort of the cosmic overview of this technology and these sciences.
Really, the field comes in from two directions. One is building from the bottom up, like chemistry, where we attach atoms and molecules together and then try and often make something functional or something with new properties, and then also sculpting from the top down, much as we've done for centuries. But in this case, we use materials like silicon, where we'll cut it up in little pieces, and we'll turn some of the parts into insulators, and some into metals, and some into functional semiconductors that make billion devices on a chip that have enabled our computers and phones and so forth.
Can you give just a quick description of the difference between gold at the scale of someone's watch
Sure.
and gold at the scale of an atom, and why it's so different?
Right. So the properties change as one goes from atoms all the way up to macroscopic objects, and in fact, gold nanoparticles have been used for centuries. I think Vicki often shows in her talks the Kyrgyz cup from Roman times, where gold appears red in stained glass, and some of you will know rose glass. So I have some mid-19th century glasses my wife got me as a birthday present, and the red color comes from gold nanoparticles that were put in the glass. So even long ago, there were nanoparticles, they just weren't called that at the time.
Speaking of Vicki, so how do they get from an application like, well, in glass or
Right.
whatever, modern application into the environment around us?
Well, actually, that depends a lot on how it's used. So if something is, in a piece of glass, you have to wait for the glass to break down. And in that case, it's a problem for many, many generations from now. But if you look at other applications, sunscreen's a good one. They're actually held in an emulsion that we rub on our skin. And so they're right there. And in fact, they're designed to coat the skin, so they're there in a large quantity. So I think what's interesting is there's so many different uses of nanomaterials, consumers, businesses, in our devices. In a device case or the glass you drink case, it's going to be in a landfill somewhere where we're eventually going to see it, or maybe in an incinerator. In the case of personal care products, we could be exposed to it every day. So I think that's kind of the range of different ways that nanoparticles can find themselves interacting with us or interacting with other species in the environment.
And what kind of work is required to sort of clarify how they move? And we'll get to the risk question in a minute. But
Well, this is the exposure questions, like where are they?
Right.
Well, so it's an interesting set of work. So they're really, really tiny. I'll add to the sort of how big are they. So I have this, okay, we're in Manhattan, right? So if Manhattan was a human hair, a 10 nanometer, which is kind of bang on the middle of nanomaterials, would be about the size of a beach ball, to give you a sense of what we're dealing. So we can see a hair on our arm, but we certainly can't see these particles. So part of the challenge is, let's say one of the places people have looked for titanium dioxide, which is in sunscreen, nanoparticles, is actually in the filters of swimming pools. So the concept is if it washes off people's skin, we can go there and look for it. The other place they'll find themselves from consumer use where they're not, for example, bound in glass, is at the end of a wastewater treatment plant after we wash our clothes, for example, and nanomaterials may come off. They get washed down the sink. They go to a treatment plant. They're not going to be treated there. They're not going to break down, and they end up in the sludge, which is often used as agricultural amendments. So that particular area is one that's of great interest, the interactions of the materials with plants and what happens when they get into soils. So these are not things that you're going to smell. The one thing I can say about most nanoparticles is I term as a chemist, they have no vapor pressure. They're not going to loft into the air. Really, they're things in our food. At least the examples I'm giving, we can talk about aerosols. But most of those applications we're worried about, eventually the sinks are going to be sediments and soils, at least from a big environmental perspective.
We'll touch on some aspects of this again in a few minutes, but when I'm looking at that dryer fluff, like what kinds of things would it be unremarkable to see there?
Well, that's a really interesting question. Everybody knows their dryer fluff, right? So if you could zoom in to the dryer fluff. So a lot of clothes now are manufactured with silver nanoparticles. My grad students like to joke about it because it's if you have clothes that have silver nanoparticles embedded, they will be antimicrobial, so you can in principle wear your underwear for a month. They seem to like graduate
That's
students.
good. Yeah. My son will be very happy to
I
know that.
know. So if we value that as a society, which some of us may, then those particles are attached, but they're not like embedded in glass, and they can fall off. And when they fall off, they can end up in dryer lint, and you can pick it up, and that particle may end up on your hand. It may end up part of your clothing, and there's a variety of ways in which you could expose yourself to it, or you throw it in your garbage, and it ends up in the waste dump of your local community.
Yeah.
So the point is there's not a lot of mechanisms for nanoparticles to be degraded, and once they're in water or soil, they tend to stay there unless there's some other process that occurs.
Yeah. So now we'll move to the toxicity question. We know it's flowing around. It's in the dryer fluff. But Som is a preferred sort of shorthand first name for you, Som?
SOM.
S-O-N?
Not something else.
Oh, yeah, okay. Oh, I see. You said your students sometimes call you something else, but we won't talk about that. So toxicity, how do you go about, how did you become interested in this question?
Well, the whole nano, I got interested when I was a child, actually. You have something called a plant, touch me not plant.
Yeah.
When you touch it, the leaves will fold and the stem will drop. That's because there is a nano structure, there is nano cells here, and the water is squeezed from it, and it is brought down. And that's where I got interested first, and of course I didn't know why. And also some of the animals, like chameleon, can change its color because of the different nano cells on the top and the middle, and the pigments get mixed. And so in nature, there is always nano at play, and it has not been harmful, and only maybe the engineered nanoparticles are harmful. Or if they were harmful, we were immune to it. We got used to it. The nano is not new. Nano has been there for centuries. Like you mentioned, even before that, nano has been there. So question is, with the engineered nanoparticles, how do you mitigate the toxicity? You asked what is the opportunity. I think that's where the opportunity is. Making and following, there's a lot of work done already, how to mitigate the nanotoxicity, and then how to use it even for imparting and using drugs in brain, to cross blood-brain barrier. That's where the opportunity is. You have a lot of nanostructures in brain, and how can you influence it? But also, I'm interested not only in nano in size. Mm-hmm. Most of the opportunity in my mind is nano in time. You go to millisecond, femtosecond, things happen. When an atom comes towards each other in less than a femtosecond, they react. And we know very little about it. Sure. One Nobel laureate who got Nobel Prize following that, he died recently. I think that's where the greatest opportunity is, because things happen so fast. That is nano in science, nano in space, not in nano space, nano in time. They're temporal.
Hey, by the way, is that part of the difference between a substance at a larger scale and a substance at the atomic or molecular scale, that the reactions can be faster, that the way it reacts with other materials or whatever?
There's more surface.
Well, you could.
Well, there's more surface area.
Sure.
And so you can take advantage of access to the atoms you're trying to use that way. That's why in catalysis we try and disperse the material we're using, and often those are expensive, and so a more efficient way to use them is to make them little, so more of the atoms are exposed.
So the smaller, dicing something up gives you more surface area for the same volume and more reactivity?
At some point, it's all surface. But also the properties change as you get smaller, and you can use that to advantage as well.
Yeah. So I guess the atom is the smallest, most surface.
But you have to hold it usually in some way. Yeah.
And
So we usually support it on something else. Yeah. Yeah.
So where would you look for, in toxicity questions, I think we all start to think about ourselves, as a consumer first, but what about occupational exposure? I assume, is anyone studying the sweater factories in China I would assume the first place you would want to look to see if there's a human impact is not in our households, but in a manufacturing center. Have you looked at that?
Exactly, the waste material, electronic waste material that is sent into China, and they break up, and without any kind of protection on the mouth, they break, and the toxic materials, cartridges and everything is breathed all the time. That's where some regulations are not there. Regulations are not here either in the manufacturing and transport of material. Not as much regulations there, but there a lot of people are getting affected. And nobody's following it, but they have to make a living, and then the residual material is dumped in the nearby river. So that's China and India. Yeah.
I would say the first place you look is in the laboratory, not in the
Actually, that was what I was
manufacturing
gonna say.
process, right? We have experiments we can do that'll associate classes of materials with risk or safety, and so we can design the materials that we use in manufacturing and those processes to keep the people working there and all of us later safe.
Wait, are you talking in the laboratory? You mean in terms
Doing
of
experiments.
knowing that there's a pathway that could produce
Well,
pathology?
that's right. So choosing the materials with safety in mind and choosing the manufacturing processes with safety in mind. So there are, that's a big effort. Vicki led one of those before she moved to Brown when she was back at Rice University. Andre Nell at our university and a number of other places around the world study exactly that. Are there classes of materials that we can proceed safely to commercialization? And are there others where we need to understand more about either the safety issues or define the materials themselves better to understand which would be safe to use and which not? And really we can guide technology development by the results of what we learn. The exciting part of nano is it's at the scale of function of biology. Sam mentioned that already. I'm married to a neuroscientist who likes to say, well, the brain's always been nano. Where have you people been for millions of years? And, when you study the biological interactions, some are bad and some are good. And so there are tremendous potentials for therapies developed with those biological interactions. And part of the fun, really, is going in and saying, okay, well, not only are these materials safe, but they're protective in some ways.
So, Vicki, can you talk a little bit about the work that was just described there?
Yeah, so I think of the concept of safety by design. So if we go back, I think I got into this concept because I was reading in the ACS, American Chemical Society, our publication, C&E News, had just done a study of, like in the 1990s, why people don't become chemists. And it turns out it's the least popular science, especially for parents. They don't want their kids to become chemists. And one of the reasons is the association with pollution. And I'm like, well, that's terrible. Why is that? And you sort of go back in history and you can see chemists solved, really tough problems by developing new kinds of chemistry. But then there are always these environmental gotchas, right? 10 or 20 years later. And so it had been associated with that. So the concept, I think, that is a lot of green chemistry, safety by design, is maybe chemists, if we start asking ourselves really early when we build anything novel, whether it's a nanomaterial or a molecule, hey, I know this is going to do something really good, like, for example, be a great insecticide and wipe out malaria, but on the other hand, how might I also think about ways it could be bad? And then could I get the good part of it, the functionality I want, by also minimizing what I know could be dangerous. That means we need to know the science well enough to know what makes something dangerous. So among all of our nanomaterials, which ones are going to be sociopaths, so to speak, and how do we train them not to be, if you want to use that analogy. And I think that concept that a chemist as a maker, because that's what chemists do, has a responsibility to think about what might be the consequences of a novel material or molecule, and also what might be the benefits. So we do both together, and it's an interesting sort of balancing act because the two disciplines of toxicology and the applications areas are quite distinct, although fundamentally very related. But I think that's the concept. So I can give an example. It's actually in our sunscreens. So the material, this gets back to the surface, titanium dioxide absorbs ultraviolet light, which is what protects our skin from radiation of the sun. So that material is nanoscale. And the reason that's a good thing in your sunscreen is it's not white. Who's old enough here? I can't see the audience, but remember where we used to put the white on our nose? Yeah. That's because those titanium dioxide particles were huge. They were like big boulders. And they scattered light, and they kind of felt chalky, right? So you consumers love it when you have clear, nice, smooth sunscreen. And that's the nanoscale, but it's still absorbing UV. The problem is it's now small enough that it can interact with your body in ways the big boulder couldn't. And in particular, the other thing about nanoscale TiO2 is it's highly reactive and under UV light can form nasty free radicals, which was the point of putting it there in the first place. So in any case, the safety by design solution is to coat it. It's like a peanut M&M. You get the titanium dioxide in the middle, but you don't want that reactive surface. So you put on the surface an aluminum oxide coating, which doesn't affect the UV absorption, but it precludes the chemistry from happening at the surface. So that's, I think, and in fact, many, but not all of the manufacturers of our sunscreens have gone to that route to sort of get the benefit, but then going that extra step and some extra cost to make it a bilayer material or two-component.
Paul, I want to go back to you a little bit on, just to make sure we have a clear picture of the landscape. Which, in the magazine, in the journal that you edit, when you look across which sectors of business are most in this arena, or like how much funding is coming, how much of it is oil, renewables, clothing. Can you just remind us again of the landscape of this?
So we had a whole panel last night on energy, ranging from capture and harvesting and conversion to storage, transmission, and so forth. Those are enormous areas. Electronics has really been a driver. Drugs to a smaller, because there's a lot of research. There are only a few drugs that are in the clinic now. There are more in trials.
It would
there's
seem
an
to be,
opportunity.
it would seem to be an arena where there'd be a lot of potential, because a much smaller amount of something.
Not just much smaller amount,
yeah.
but you can put combination drugs and timed release together. Part of the problem is, how do you get those approved? So there's just working backwards, trying to make the simplest nano delivery system he could possibly make. Mark Davis at Caltech put together a nano delivery material that only required 61 volumes of reporting to get approval to go to trials. Yeah. And when people make much fancier combinations, given the way things are now, it's almost unimaginable that one could take those all the way to the clinic. So
that reminds me of something I read in preparing for this, which was that just looking at gold, that there's like someone did an analysis that showed that there's the responsiveness or issues around gold, or what was it called? At a certain level, like a mid-level, there's more impact, and then less.
Yeah,
and then,
it's like
so
it's like Goldilocks. Too small is good. Too big. It's
which
like
would make a drug issue. As you say,
things that make it a good drug can also get people queasy about potential risks. And I think the FDA examples are good ones, because there you have a regulatory process that's very adept. Well, I won't say adept, but is set up to handle novelty. Because it's constantly evaluating new things and is constantly weighing risks versus benefits in a particular way. And it has, it's been incredibly hard, especially for the more exciting nanomaterials, to get through those hoops. And unless the disease it's curing is, has no other, people have no other hope. So there are certain cancers in which there's been more progress than sort of chronic disease. But I think that it's an interesting case study, because when we looked at examples from our center at Weiss of things that were moving into human trials, it was on the order of about 12 years from when those first papers saying, hey, this could be a possibility, to when it even got into human trials, which is much slower than, probably about a factor of 2 slower than other materials. Yeah,
regulation is really set up to work on chemicals, which can be precisely defined in general. And when we make new nanomaterials, they're usually mixtures. And often when we manufacture them, it's going to be easier to make a mixture than to make an absolutely atomically precise structure. And so if you had to treat every new nanomaterial like a chemical, we don't have enough money and we don't have enough animals in the world to do the required testing. And so we have to become smarter about that, and that's one of the places where that hierarchy of trying to define groups of materials that appear safe and can be tested together, hopefully can be commercialized safely, and we can do those more defined experiments both on the material side and the testing side as needed to develop other
safety by
materials
design,
and apply them.
Can you talk a little bit about the work you've done on nanoparticles and how they behave in plants and soils and stuff like that? Yeah,
soils are fascinating, so I may go off a little bit of a tangent here. So plants are remarkable living systems because now I'm not a plant biologist. I was fortunate to work with some really good ones, like a lot of nanoscientists. And what they do is they are really good at mobilizing what they need from the soil, and they do that in partnership with microbes that grow at their roots. And so when a nanoparticle ends up there, remember I said the reason we're studying plants is we're pretty sure that's going to be a sink for a lot of nanomaterials coming out of wastewater treatment. So consumer applications and others, that's where they'll be. And so what plants can do is you sort of have this image that there's an organism and there's a nanoparticle and they're going to interact, and the nanoparticle is going to kind of stay the nanoparticle. But actually the chemistry that happens in the roots, not even in the plant, but at the root system, can be very aggressive. And it can actually dissolve and break down nanomaterials quite quickly. In a way that we don't see in other organisms. And so one of the features of a lot of the emerging nanoplant studies is that if you've got nanomaterials in soils and they're really close to root systems, they're going to dissolve. They're going to become soluble, and the plant is going to try to extract elements from that. And that can be a good and bad thing depending on the plant system. The other thing we learned is that most plants don't take up whole nanoparticles. Plants are very tight. They've developed a lot of defenses against plant viruses, which, by the way, one of my favorite plant viruses, cowpea mosaic virus, is a 15 nanometer sphere. So the only way you can get into a plant is with an insect punching a leaf. So plants have actually, they're quite difficult to get into. And their modulation of the plant's activity at the root system seems to be the dominant issue. And also, plants draw enormous amounts of water from soil. So my colleague was doing work with cottonwoods, and they would just draw all the nanoparticles, this huge pressure. So you could have them everywhere in the soil, but they get pulled just because of the water flow into the plant root system. So the exposures accumulate at the roots where they undergo. Now, the one really not such good thing that I think can happen is some nanomaterials are antimicrobial. And the microbial communities in plant root systems are crucial for doing what they do.
Right.
And so when that gets knocked out, the plants get extremely unhealthy. And that's really the primary way that you can affect agricultural productivity. But you can also see with some other materials, you can get, actually plants grow better. We had one experiment we did where we saw an enhancement of our plant growth, and that was partly because of the minerals that were getting released by the nanoparticles.
Is there a prospect? Sorry.
One important use of nanoparticles in agriculture. One of the main problems in agriculture is nitrogen utilization efficiency. Lot of fertilizer is put wasted, and that nitrogen utilization efficiency can be improved by using nanoparticles. By that I mean you deliver nanoparticles to the root to deliver the nutrients and nitrogen there, so that on the top it's not wasted. And I think you mentioned the enzymes that the roots generate can extract things from the nanoparticles if the nanoparticles are properly designed. There's a lot of opportunities there.
Well, this is good I wanted to shift back into the prospects. We've talked a lot right now already about, some of the questions about impacts, but, risks and benefits, trade-offs is always there. So is there anything else in agriculture? That sounds like a pretty interesting idea, because precision delivery of anything is what you want.
Another thing is to imitate. We have a biosolar project to imitate the plants, what the plants are doing. The leaves collect the photons and convert to electrons. That all depends again on the nanostructure of the leaves, and how do you increase the efficiency of conversion of photons to electrons is the problem. They're efficiency is very low.
Right.
We think, people think that in general by controlling the morphology of the enzymes, the way they dance with each other, right, I think the efficiency can be increased. By the way, another use in the area of energy, I have a project called carbon dioxide to champagne. Carbon dioxide is no problem, but carbon dioxide to champagne. Carbon dioxide can go into carbonate, to formate, various alcohols. They all have pathways with activation barrier. If you can selectively decrease the activation barrier for carbon dioxide to ethanol, we all like ethanol, right? or formate is better, ethanol. Selectively decrease that activation barrier, that will be very good. And we can do that using copper nanoparticles that are doped. Why copper, we don't know, but doped. That again shows the heterogeneity. There are doped means only few atoms of whatever you dope with in the copper does it decrease the activation barrier, and carbon dioxide go into formate or alcohol. So that's a good example of the beneficial use of the heterogeneity. But
right.
We have to know that.
So I wanted to talk to you more about medicine. We talked about medicines, pharmaceuticals, but where else in medicine can this play a role in healthcare generally?
Yeah. So, I mean, just in sunscreens, a simple example, we can build in capabilities to nanoparticles that we apply. There are tremendous opportunities in diagnostics, so we can, have sensors that we put on as called temporary tattoos, but they're really stickers. There's one that's just being distributed now to look at your UV exposure. I think L'Oreal's giving it out in a dozen or so countries to say.
So it's like a cumulative exposure thing?
Right. Right. And so these, a lot of people have Fitbits, I think.
Yeah.
Vicki has one on, or some equivalent,
actually, yeah.
right, that measure exercise. There's a lot more that we could measure. You can tell when someone's dehydrated for athletes. There are sweat sensors that can see that, the composition of the ions coming out of you are changing over time, and that can be an alert. You need to stop at the next table in the marathon to pick up more water, electrolytes. They're
The
very
great
big.
opportunity, I think, is in medicine is delivering where the cancerous cells are.
Okay.
I use the example of when you take aspirin, you have no side effect. But when you have chemotherapy, you lose the hair and everything.
Right.
But if you can use that chemical which can kill the cell only where the tumor cell is, then chemotherapy will be just like aspirin. And it is possible now. People like Bob Langer at MIT has shown that using nanoparticles, it can go there and attack where the tumor cell is and no other cell. And that will be really the holy grail, I think.
I don't know.
Attack where the damage is.
I would
Vicki?
say, I would think a little bigger. I mean, first of all, I'm not sure we can make a heat-seeking missile yet to a cancer
But
cell.
they can.
I
We
would
call
argue.
it missile drugs.
Yeah.
Bob
But-
Langer does it. A lot of people do that.
Yeah, but their efficiency is pretty low, meaning if you take a dose, it's
people are
better.
alive. I know people who are alive because of his technology.
No, I'm not
Yes,
saying
yeah.
it's not. I'm just saying we should be, cautious in saying that 100% of the drug goes to the cancer cell because it's rare that happens.
Okay, 100%.
100%,
But
yeah.
it is true,
But-
side effects can be reduced
Yeah.
by,
And I think it's a good
delivering
thing.
properly.
Uh-huh.
But I think really, kind of one of the other themes of this festival that I think is really an interesting question is if you're going to make materials, artificial materials, and integrate with our bodies, and that's really what we're starting to do with these devices, like actually become part of it. What is that interface going to look like? And what we've been doing to date is taking large boulders, macroscopic materials, and shoving them into people's bodies. And of course, the body is not happy with that. It's got a lot of reactions to having a macroscopic element put inside of it. So, my hypothesis is that actually nanostructured materials are the ideal thing to help us make kind of the seamless integration between the artificial world and the living systems. Now, doing that has a lot of consequences and presents a lot of challenges, but I believe that that's what, if you were to go 50 years in the future, you're going to find the tattoos or, implants in the brains or, our clothing, the ways in which it will interact with us will be largely defined by materials with nanoscale structures and dimensions.
What's furthest forward on that front already? Is there some particular niche?
Well, I'm looking at Paul, seeing if he
Yeah,
wants to
that's-
pick one of the sci-fi examples or if I should.
Yeah. Well,
I'll do it.
there's plenty of accessible space on us. So, for instance, there are 200 or 300 species that live in your mouth.
Right.
Some are protective. Some turn on you and give you cavities or root cavities. Or if you are going to get a periodontal implant, they are going to eat around the implant. It's going to fall out. And dentists and periodontists know that, but they don't yet have any reconnaissance for those species. It isn't that difficult to imagine when you're getting ready for an implant to get a swipe and check if you have that bug for the month preceding. And so those kinds of things will come, I think, much sooner than the 10 or 20 years. I'm hoping, in the next few months we develop the technology and then that gets out there very quickly thereafter.
I'll give you the other example, and you'll have to tell me how sci-fi this is. But for example, we were just talking about this before we came on. The number of people now and the opportunities in neuroscience and neurology for the implantation directly of electrodes into people's brains for treating disease. And the problem with that is many problems. But if you could make those electrodes highly conductive and also flexible, that's something that biological systems are very mechanically sensitive. Almost all examples I've seen would tell us that. And so if you can integrate those electrodes and make them less foreign to our brains, then what you're going to find is they last longer, they have less side effects, and that's something that you can do by manipulating material structure on the nanoscale. I mean, that's a far reach, so I'll look at Paul
Yeah,
and say,
Vicki's very kind because
Yeah,
that's
yeah.
something my wife and I work on
yes,
together.
I
so,
know,
yeah.
I know.
Well, that reminds me, I'll just ask this out of the blue. When I did my master's thesis in journalism at Columbia, it was on organ transplantation, the future of organ transplantation. I did a piece about a profile later for Discover magazine of an organ transplant recovery coordinator. And lately I've been tracking the literature on, because as we move to autonomous vehicles and stuff, the number of donors is going to become it's already a problem, it's going to be a huge problem.
right.
So is there any role here for anti-rejection with organs?
There's several things in transplant. So our hospital is sort of built on the back of some fantastic transplant surgeons, and we have a problem right now in terms of harvesting organs that someone's in a motorcycle accident and they get cut up and shipped to a bunch of different patients. In Singapore last year, 6 people died from one donor from infected organs, and
Wow.
that's something that happens regularly. There's not time for reconnaissance on the from the point of collection of the donor to implantation.
Yeah.
And as if you follow transplantation, all kinds of things happen with immunosuppression. We basically give an artificial cancer to many of the recipients that leaves them in the hospital for months afterwards under protection because of their first compromised immune system and then the diseases that we induce. And so there are all kinds of opportunities there and connections being made really between the transplant surgeons and the the people in nanomedicine to try and overcome some of those issues.
Interesting. One thing we were talking about earlier backstage was how your specializations can have potential value in a host of different disciplines, and you tend to float. I think when you talk about floating, it seems that collaborative approaches to the science and innovation seem to be vital. I would thought maybe I'd be curious for each of you to describe whether you've had an experience where that's become manifest. Vicki.
I mean, I think if you're a nanoscientist, you actually are a collaborator. The field was sort of started in that way in many ways. So what my interesting observation about collaboration is I sort of say 2 things to my students because virtually everything I do is collaborative. First of all, different disciplines present different challenges for collaboration. So I've learned through being a nanoscientist that dealing with toxicologists, they have a culture and they have a thing that so there's a value system that comes with your core discipline versus dealing with physicists. They're going to have completely different sets of issues. So part of working well and understanding these disciplines is to know what are they going to really care about and how do you, so it isn't just communication and terminology, but it's understanding what am I going to value. My core training is as a chemist versus what they're going to value. And there's something about, I think it's shaped when people are undergraduates, this sort of disciplinary identity and reinforced in graduate school. So part of the gulf is to share of, what's going to be important when you do science, how many replicate experiments are you going to have to do. And of course there's the language, figuring out, my favorite example in nano is if you're a chemist, you learn how 2 atoms interact through something called bond theory. And if you're a physicist, you learn solid state structure. And they seem very different, but they're actually the same, right? And so the field, I think, revealed that as those 2 areas came together. But it is really, I think, a matter of really appreciating that even though science is objective, disciplines have value systems. And part of effective collaboration is kind of understand, I'm working with a surgeon. They're going to be really focused on a quick tool, and they're going to be very focused on patients, as opposed to dealing with
and they're going to be very
physicists.
egotistical.
And they're going to be very busy.
I haven't met one who
and they're
isn't.
going to be very arrogant and willing to
Right.
try anything in my, limited
Right.
experience. And I think as scientists, we sometimes don't want to talk about, culture within science or the personality elements. And I don't know if I'm going that far, but I think in collaboration, it's really revealed to me how important that is. And when you get that right and you understand them and they understand you is when you usually are able to have a really great working relationship and make the progress you need.
Now we're going to move into this sort of the interface with society more generally. couple things that come to mind. One is to ask you which lessons from history worry you the most when you think about where nano is going to go now, whether it's looking at what happened with DDT or more recently with GMOs, where you have this Monsanto effect where many people have a concern about GMOs. It's really their concern about industry or about something about a particular company. And a lot of the interests in this arena are corporate as well. So I don't know if you each have a sense of kind of like your worry about how this is going to play out going forward.
Well, I think the whole reason we're here is we're trying to take a thoughtful approach. The field has established some of the leading investigators who work at that interface of materials and safety, as well as new materials and medicine. When you do essentially the same measurement looking for positive and negative effects, and so really what you're doing is sorting. And when you combine those areas, you learn more of the biology, and you're able to do an end run, maybe around the complete characterization in some cases, and then identify where one needs to know more. And I think the next step for the field and commercialization is making some choices as to which technologies to push based on the results. And I think we're right at that crossroads now, where we have so many different possibilities in so many different areas of application, that if we put that in as part of the feedback loop, then that's where we avoid the missteps of other fields in the past.
In that regard, what is important may be asbestos was very good for insulation and everything. It was good for the society. And then there was asbestosis. Just want to make sure there is no nanosis around the corner.
Nanosis.
And if you ignore it, and if you don't have developed technology to mitigate it, then there will be nanosis. And there will be, I suppose, you spend more money now to remove asbestos.
Right.
And nanoparticles are going to be even harder to catch. So I think that is what that we have learned from asbestosis and coal, whatever that term is, pneumoconiosis or whatever, silicosis, and all this. They're all good, all these good materials. But they had bad effects, like you said. You have to also know the side effects. And even medicines have side effects. So we have to swallow that, but try to control the side effects.
So this gets back to the safety by design paradigm. Can you do better? Do we always have to learn by going, we didn't think of that?
Yeah, I mean, I think my worry is sort of twofold. First of all, even though we're talking about nano and its risks, it's actually kind of a laboratory experiment for the first time. A discipline is really trying to get ahead of the curve, since we know that technology has unintended consequences. I mean, I can't think of one. Maybe somebody will come up with one that is all good and everybody loved it forever and ever. But my sense is that we're kind of trying to figure out how it works. And
Chocolate.
Chocolate? I'm sure, no, I get migraines with chocolate, so I'll fight you on that. So my sense is that, society has to grapple, and by society I mean the public, of which I am one, we want benefits. Like, we want our Fitbits, and if you sold me a Fitbit that worked better because it actually was part of my body, I would probably buy it. But, it's so the consumer demand for better sunscreens that are not white and chalky is sort of what's driving this process. And I think that's partly an area that I wonder how consumers are going to be part of this, and saying, hey, I want a label, or I want this to slow down. Here's where I'm willing to accept a risk. Here's where I'm not willing to accept a risk. And I think that there's a challenge there that I worry about, which comes actually with labeling, because I don't think consumers know necessarily. And I think that's keeping them out of some of the ways in which they may influence this large sort of corporate academic sort of train that's left the station, so to speak. On the science front, this is a broken record, I'm gonna worry about the field moving too fast towards trying to do testing rather than trying to establish the general principles by which we can do safety by design. So if you've got a product that's got a sunscreen, you want to know, how do I know if it's toxic? And that does us no good in helping us design it more safely. We actually have to do a little bit more fundamental science, and it is extraordinarily hard in this particular climate. I didn't mean to say climate. I was going to try to avoid that word. To try to make that case for slower, more methodical work that is linked to that potential. And I think going too fast, you won't be able to develop these really fundamental mechanistic understandings that you really need to do effective safety by design. So I think that's my scientific worry.
But San, this gets back to something you kind of mentioned in passing, talking about sunscreens, that there are natural solutions that might be a bit more beneficial. But often, if you're a company, a big cosmetics manufacturer or something, your interest is efficiency and production and profitability and consumer confidence. But it might lead you in a direction that wouldn't necessarily be, in the end, the best choice for what you're talking about. When all the money flowing into the field, how much of it is related to the sustainability questions, or as opposed to the, boy, can we manufacture sweaters more efficiently now, or whatever?
When a while ago, at least 4 years ago, the consumers were wanting more green products. But when the economy became bad, they got away from that. But there was a survey done which showed that the consumers wanted green products. There was a US news, I remember the cover says, "Go green or go out of business." There was a cover page. And that was consumer driven. And that's because there's an association in UK which showed that every sample of breast milk analyzed showed cancer compounds. Not 99.9, every sample of the breast milk analyzed some carcinogenic compound. So when that came out, along with some other company which marks red, blue, green, then consumers are driven that way until the economy is suffered.
Yeah.
Let's go back to cosmetics for a second.
Sure.
Because for me, those are a great thermometer of public perception. So
Right.
I'll tell you a secret, I like going to cosmetics counters. And when you go to them in the US, nano's used for promotion of cosmetics. And if you go to cosmetics counters in most Asian countries, you charge more for things that are nano. And if you go in Europe, you don't mention nano. And that's something that we as a community are trying to address. So exactly the association you made, that people don't think of nano as GMO, but have an understanding of what it is we're doing that isn't supplied by a science fiction writer. And it is really a race right now for that public perception. Well, let me talk about another field for a second. So plastic microspheres are being taken out of cosmetics because of the environmental consequences. And the replacement for them may well be some natural nano products. There's some that are being tested now by a number of different companies that will be biodegradable and safe ways to deliver the cosmetics that don't have any of the consequences that the plastics do. So I think you'll see those. As soon as one can scale up the production.
The opportunity in biodegradability is great, but it is controlled biodegradability. In other words, you don't want to make it and biodegrade tomorrow. It's going to be in the shelf for 6 months, 1 year. So you want to biodegrade in maybe in 1 year or something when it gets to the river water and so on. So the controlled biodegradability is the key opportunity, I think.
So this brings up something else, which is you mentioned Europe, the difference in Europe in perception and here and in Asia. In dealing with all these issues, GMOs, nuclear power, I assume CRISPR, genetic technology coming forward. I think we would like to think there's one sense of what the precautionary principle is, but I've yet to find it. That everyone in this room might have a somewhat more common sense of precaution when they look at technology and innovation because they're sort of a select audience. But that you look at the global landscape and it's all over the place. So there will be opposition. There will be people and organizations that will come at you in a hard way. I've seen in the literature already. And then you see headlines. One piece that was in our background briefing from Business Insider from last year talks about this is the Patagonia fleece finding, how much of this fleece is out in nature. And it says, a shocking amount of these fibers, more than 64,000 pounds, into oceans and streams every day. But 64,000 pounds
very small.
over a lot of oceans. And then you get to this question of actual measurement of impact is different than measuring the presence of something. But it's going to be a fight. There will be.
But it's less likely to have opposition from the East, because I think the Eastern culture cares for the human beings and plants and bees and so on and so forth. I think I'm not saying Western doesn't, but Eastern seems to care. For 5,000 years, they have been studying conscience and soul and things like that. I think there will be less opposition from that part of the world wanting to care for the planet, leave the planet better than I found it.
Yeah.
So, but there may be opposition from some countries, but as a whole, it may be less.
I mean,
But as a manufacturer, it must be hard because Europe, even on standard chemical, they require testing on chemicals that we let right into the market
Yeah.
now, right
I
now.
mean, I think some of the most compelling social science I've seen on why cultural differences are there, and this is kind of a catch-all word, but sort of intuitively made sense to me, has to do with trust. So how much the public trusts in their government's ability to regulate, in the sciences, in the sort of academic systems, ability to be independent, and how open the society is are all factors that kind of govern whether or not the public will accept a risk, because the reality is they're kind of trusting a variety of different stakeholders to tell them what it is and to inform them, right? And I think that in Europe, they're really not very trusting. I've been in these kinds of panels at Europe, and it's a very different kind of feel.
And that's why we're doing this.
Yeah.
Right. So if we can, not only show how we're proceeding, but also listen to what concerns are, then not only can we address those, but we can learn something about how to proceed and what more to do. It's really a conversation, even though you're all sort of blocked by bright lights right now.
Yeah.
But I would
You will be
say-
part of the conversation in a minute. We're going to go to questions shortly.
But I would say the one thing that I can say, and it's funny when you're a scientist, you don't like to have a policy statement, because my job is to create data and not to make policy. But there is one area that I do feel strongly, and that is actually labeling on products. And I've had a lot of arguments with corporate folks who say if we give people information, they'll just get afraid. And we don't even know how to label things, which that second point is true.
Right.
The first point, I don't know if I buy. But I think that sort of openness and saying, these are the ingredients that are in this product, and let the public have some important insight. I think without that, there remains this, I can't control the risk that I personally am assuming, that I think is always going to be in our way, particularly with consumer products. So I've been pushing for a while on this one with not a lot of success.
This came
It's
up.
the one soapbox I have.
Well, this came up in a big way with GMOs. And still, the problem was a lot of the labeling initiatives that came up at the state level were implicitly punitive. They were there.
Yeah.
They were there to add, and in other words, this is the question you just sort of made, the point you made about, well, what's on the label? Is it just X is here, or is it implying this is a danger?
I think that this community, because of what we have and the nature of our materials, I think we could probably, if we had a really good working, people work together, I think we could deal with that issue in this particular setting. But I agree. I mean, is that a reason not to label, or is it a reason just to work really hard to make sure the labeling you do is accurate and informative to the people who need it or would want it? So from my perspective, I don't think it fans the flames, but I'm certainly aware there are others who think it does. So I think that's one really interesting point, and I see very different perspectives in both the scientific and corporate community in different parts of the world.
Yeah, by the way, another area where this came up was with fracking, the fluids that are pumped into the ground. Industry was resisting saying what was in them, and that led to this whole suspicion factor. Then Wyoming, a state that's
Database, right?
yeah, Wyoming was one of the first states, even though it was Cheney state, it's an oil and coal state, to move forward with requirements for open listing, and it's all there for people to explore. I'd like to start to think about the questions and answers.
This one's for Vicki. Do you use sunscreen? If so, which kind and why?
Consumers Report had a really good, it was one of my favorite collaborations with an NGO. We worked with Consumers Report on analyzing sunscreens, but this is 2010. So I have kids, right? They're teenagers now. After doing that work, I never use infant sunscreens. Don't use anything that says infant. And I tend to go for big brands that would have a lot of money. I can't name them because they're legal issues, but if you come talk to me afterwards, I'll give you. The other thing that it caused me to do, because I actually didn't know this data, but sunscreen washes off. And in fact, to get the full effect of it, you really have to reapply it a lot. So what it actually caused me to do is when I do go to the beach or go hiking in the desert with my family, I actually am really into finding the lightweight clothing and sort of covering the body as much as I can. And that actually keeps you a little bit cooler too. So my kids,
What a novel idea.
like
An umbrella?
yeah, I mean, umbrellas go a little too far for my teenage girl now, but I think that they both, cover up a lot, and that's actually net safer because the reality is, unless you're going to be putting sunscreen on every 30 minutes, you're probably going to be losing the benefits anyhow.
I don't use sunscreen.
I
don't need it. And and there's an opportunity there. Why don't I need it? What is the mechanism there
That's interesting.
that prevents the UV absorption and melanin or whatever? That's where the opportunity is.
Getting to the root of biological possibilities. I got to ask you though, why not the infinite? What was the infinite issue?
So you remember I talked about safety by design? So we analyzed, and you can read all about this in consumer reports. I'm not kidding. So we analyzed the pigments, and we tried to determine whether they were the peanut M&M types. Did they coat their pigments? And did they use zinc oxide, which is cheaper and has now been found, as we identified, to be even worse than the bare titanium dioxide. The infant sunscreens, by and large, didn't coat anything because of a variety of issues related to new formulations. And you never want to put a new formulation into the infants. They want to kind of go with something they've been using a longer time, is how it was explained to me. So when we did the analysis of anything geared towards babies, we actually found the materials they were making 10 years ago. So I was surprised by that finding, but it was pretty consistent across the board. And when I asked, they said, oh, well, anything infant, we use tried and true, in this case, was actually not really great stuff, in my opinion, And so in general, though, I think the other thing I don't like to do, we did some really, this is going to sound strange, but you can get sunscreens from natural sources and sort of the not so standard brands. I would not recommend that. We saw a lot more variation. So the kinds of pigments you need to purchase are more expensive and they're harder to formulate, so the suspension feels good and lasts for a long time. The big companies know how to do that better. So.
Next question.
Yes, could you mention the companies that are likely to benefit from nanotechnology?
Is that an investment-oriented question?
Wow, who won't?
Large companies such as Monsanto and the BASF are already using it. BASF, in fact, one of the ones that came up with the brush that you can use to remove dust, but then they had to back off when the nanotoxicity question came up. And the companies which make skateboards and so on, to make the skateboards much better with less friction, they benefit. But I would say in the future, probably the small startup companies, like the one I mentioned, probably has more opportunities to make new products and so on. So already BASF, Benz cars, maybe I shouldn't promote any company, but Benz and such companies, they have scratch resistant, and also it glows very nicely. So those companies are already using nanotechnology for better purpose. There are many others. Drug companies, of course, many drug companies are using for delivery of drugs.
Yeah, really, in medicine, it's the little companies that are doing the exploration, and they're going to get purchased by larger companies. So the ones that have, moved forward are into trials. You can keep an eye on in terms of therapies. There are tremendous moves forward in diagnostics. Energy storage companies, whoever makes the more efficient, faster charging, larger storage battery, right, is going to be there for the people who want electric cars and home storage. It's an enormous potential market.
I think the question is which companies won't, but one of the sectors that when I lived in Houston for many years has really adopted, it's actually gone much more R&D oriented, is actually the oil and gas, the traditional oil and gas companies. And what really woke them up was actually the development of natural gas and fracking technology, because it really shifted their dynamic, and it was fundamentally a technology not a breakthrough, but a sort of coordinated thing that happened that made it possible. Yeah. And ever ever since about 2007, 2008, they've taken a much more aggressive stance looking at incorporation of new materials and, everything from IT to nano into everything that they do. So the efficiency, particularly I think in the natural gas areas, both for storage and extraction, is something that those companies are strongly focused on, because they now see that it can really benefit their bottom line, which they didn't see that 10 years earlier.
Yeah, they were kind of stuck in their ways and just making money pumping stuff out of the ground for such a long time.
It was fracking that woke them up, because really up until then it was like exploration. Could you identify where there was the most oil? And if you were better at doing that than your competitor, you were more likely to make the best bet. Now it's kind of the Wild West and the very different forms of carbon-based energy that are available. I'm not saying it's a good or bad thing, but it exists.
Yeah.
So if it's going to exist, it's good to make it more efficient and allow them to extract cleaner fuels more efficiently. So I think that sector woke up pretty recently and continues to invest heavily, primarily in efficiency of extraction. They've always, and maybe there'll be a breakthrough in exploration based on nanotech.
And
Well,
after the
catalysis
oil
and
spill-
oil
Oh yeah,
refining.
catalysis.
And
Oh,
oil
and
refining
refining.
has been there.
Yeah.
Yeah.
It has been there for decades, and one of the innovations I particularly like is the idea of using nanoporous materials. In part because the guy at Mobile who did it has the same name as me, Paul Weiss, who was my colleague back when I was
I
at
didn't
Penn
know
State
that.
SZ. But
Yeah,
that's
that's true.
that dramatically increased the efficiency of oil refining and the energy content that we could get out of what we took out of the ground.
that's a guy-
And so those advances preceded much of what we call the field of nanoscience and nanotechnology.
And
But-
after the oil spill in Gulf of Mexico,
Oh, yeah.
they used some material which some said toxic. The
Right.
company which made it said it's not toxic. Then there was an opportunity for companies to make, again, proteins, bioproteins, which will coat the oil particles in such a way that they will stay in nano form for a long time. And why is it good? Because microbes have an opportunity to eat that oil. So this kind of nanofilms of oil droplets had an opportunity which some companies used. That's where I got into the Stephen Hawking's episode of Brave New World.
Interesting. You mean when the oil is in smaller amounts, it's easier for the microbes
Well, there
to
are many
break
ways
it down?
by which they burn up the oil. That's one
Yeah,
way.
yeah.
There are many ways. One way is to use the microbes to eat the oil.
Right.
Well, for microbes to eat the oil, there has to be a lot of surface area of oil droplets.
Right.
For that, you have to have the oil droplets in nano form. So what you do is these biosurfactants will coat the nanoparticles, and the film is so robust that it will stay as an emulsion droplet for a long time, and the microbes can eat it.
Okay. Another question.
There was a comment made earlier about distinction between basic fundamental research and how you mentioned that some of the problems that you thought your field faced actually required that, and you mentioned the current climate was sort of potentially not sort of conducive to that. So hoping you could expand a little bit more about whether you think that's specific to your field or in broader science, and why you think that is, and just sort of your general comments on that front.
Yeah, it's a really hard one. So I think that since I've been, it's a double-edged sword. I would take some responsibility as a scientist for this situation. So back in the 70s, there was Sputnik, and a lot of these agencies that are funding us now got started with this sort of, I call it the fear of Russia beating us. And then it sort of shifted to a hope argument. By investing in science and technology, we can have a better world, a better economy, more jobs. And that was sort of the different ways in which we decide to fund what we do. And I think in our quest to make what we do more impactful, so to link what we do in the lab, which is a fairly abstract, detailed kind of work, and to make it relevant, we're driven to make applications, right? We want to show that I didn't just say that, hey, I could use my nanoparticles as an antioxidant and use them in medicine. Someday, I'm going to show you that. And what I think that tilted is it made it extraordinarily difficult to put forward, much more difficult to find agencies and programs willing to do the solely fundamental, I would call it, I hate to use the word sort of trooper, but that the fabric of science is really the repetition, the people checking, and that's harder to do now. You have to always focus on the application, and then you have to deliver on that application, if that's what you promised. And guess what? That means you spend less time systematically unraveling underlying mechanisms. And I think that, like I said, I hate to blame other people. I think as a scientist, I'm sort of guilty of it because I wanted to, in my career, make things relevant. And I think that's shifted the field, and I think nano's been part of that. I would also say the climate, of course, is changing for that. And certainly, current administration, my early reads from my network are not positive for fundamental science. Anything that I'm going to write a proposal on has got to be, I'm going to either partner with a corporation, or I'm going to start a company, or so I don't have time, and I don't have that ability unless I can couch it and kind of do it in drips and drabs. So for me, I find that more difficult. I don't know if I'm the only one.
So we're close to wrapping up. I want to give you the opportunity to come up with a closing thought. But my question for you, my prompt for you going forward is, as I said at the beginning, we seem to be in a race between potency and self-awareness, between what we can do and what we choose to do. And I don't know, going forward, do you feel we're on the right track to get that answered in a way that people 100 years from now will say, oh, they kind of worked it out?
So I think, as you heard, one of the advantages of the community is we bring in people from other fields. We're naturally curious. We talk across those fields, and I think that bodes well for looking at the consequences and trying to explore those in advance and engaging with the broader community as well in what the issues are, how to proceed, what to develop, what information we want to make sure everybody has, and so I feel really a positive outlook for the development of the technology in a safe way, just because of that stance, really, of the people in the field and where we came from and how we interact.
Great. Son, any last thoughts?
Yeah, in terms of products, for the community to accept and so on, the companies have to be more transparent. I know they have their own obligations, and then the community will accept. But in terms of, they want to end up by saying, re-emphasizing the opportunity, where probably there are no toxic effects, are studying the nano time, nanosecond, millisecond, femtosecond. This is not at all, there is one Nobel Prize obtained several years ago. That's where all the Nobel Prize, those kids who are the Nobel Prize, that's where the Nobel Prize is.
Good. All right. Vicki?
Yeah, I think, we're probably doing as well as we could on this one. I mean, we're asking ourselves to look in the crystal ball and see the future. Yeah. And we do that all the time at the beginning of our grant proposals. We're doing this because someday. And I think now we're training ourselves to think about it the other way. And I think it's, like I said, I think we're doing about as well as we can. The only thing I would hope is that there would be a really good public-private partnership to work on the issue of labeling.
Labeling, communication.
Yeah.
Well, this has been a rich and wonderful discussion. There's lots more to be learned going forward. Thank you very much. Thank you all.